All right, so good morning, all four or five of you. Today's talk is going to be about the perversely named Widman's hole-filling technique. And hopefully we'll get around to an application of this to show Holder regularity for solutions to elliptic equations. So our general setting for this, and I'm going to try to write stuff up over here, I think, and then leave it there, and maybe over here, and then talk on that board. So for the whole talk, we're going to do omega, as usual, is an open, bounded, whatever, connected, smooth as you want subset of Rn. And just normal Sobolev space, 1, 2. Does everybody know what this means, or should I write that out? I think everyone's good, right? I think I'm the only person here who might not know what that was, and luckily we just covered that 3 weeks ago in PD, so I'm good. All right, and so now here's some stuff that I'm less comfortable with, so everyone jump in and tell me whatever, but I'm just going to use little pieces of it because whatever. So we're going to say that U is a weak solution to this elliptic equation. L is an elliptic operator. And in particular, the thing that's sort of going to get used from here, although I'll show you, in the end you can probably disregard it, is so if you write an elliptic equation like this in divergence form, you write it maybe like, and this is where everyone can yell at me if I do something wrong. So maybe something like this, where A of x is a symmetric matrix with bounded entries, measurable functions over omega. And the only reason I mention it is because for these sort of things, ellipticity, we get this condition. Inner product for some coefficients lambda and lambda, little lambda and big lambda. How's that? Oh, yeah. And so in particular, if you just think of this as the Laplacian, then these are just 1, yeah? Is that right? Yeah. Yeah. Okay, great. And then the other thing to point out here is what we're going to be talking about sort of in general is the Dirichlet energy. Of U over omega. And this is going to be given by the integral grad U over omega squared. Have you guys seen this before? This is something that's probably super not new to anyone but me. So just some properties of this guy. Obviously it's non-negative because this is non-negative. And it turns out that solving the Laplacian on omega is the same as finding a minimizer to this over omega, I think with like some prescribed boundary conditions. And so this sort of thing will give you harmonic functions, and then we could plug the rest of this talk pretty much into Farhan's talk, the first lecture, and use all his fun Louisville stuff. All right. So now what's the point? Right, so hopefully I'm going to get to an application of Widman's hole-filling technique that I probably won't have time to prove, called Maury's Dirichlet growth theorem, which gives a condition to show Holder regularity to solutions to this. And to get there, we're going to use 3 results that I should probably put somewhere that I can refer to them. So I'm going to wander too far left over here. And so our first result is just Poincaré's inequality. And so, of course, there's the normal, like, here, I'll just write it down. So, given our setting, there's a constant C depending on n and omega, such that for u in h1 omega, we have this. It's less than the Dirichlet energy. Right, and in particular, we're going to use a version of this where we're going to say let this set, I'm going to run out of space, be the set of y in Rn such that we're in this annulus between R and 2R. Right. Then we can write this. This is going to be AX R. And then over here, what that buys us is instead of C, you also get radius squared term over here. And that'll come in handy later. And just remember that this is what that is, because that'll come up again. And the proof of this, if you guys haven't seen it, but I'm sure you have, is pretty clear. You just plug in 0 and 1 and then do a change of variables to get the R squared to pop out. And then... Yeah, and then, so now it just becomes dependent on the dimension. And, all right, and so this is the version of Poincaré that we're going to use. So that's 1. And I should say, so reference for this is probably your PDE class, if it's anything like mine, or any book like Evans, whatever. And then... Yeah. Yeah. It's always uniform over always. Yeah, uniform over all R. Exactly, and that's hopefully what we'll show using Caccioppoli's inequality, which is actually this nonsense. But for some reason, I actually wrote down my main result, which explains why my notes looked very weird there for a second. Right, so we get this. And then over here. And I think that this is a little more general than what Farhan gave us, because you just did it for the equation he had was it U grad U, or I mean U Laplacian U? Yeah. So if you do it for U Laplacian U, I think big lambda over little lambda ended up being 1 or something. And then you got a 4 out in front. Right. Grad phi squared U squared. Okay. That's right. That's Caccioppoli's inequality. Okay, now back over to this guy. So we have our condition there. Now we have exactly what I had written over there. So there's a b between 0 and 1 that gives us what we just said. The energy over a ball of radius r is less than or equal to this constant times the energy over the ball of radius 2r. So yeah, and what you guys just pointed out is kind of so what's going to be the application of this is that yeah, we can bound the growth of the energy as you move, as you get bigger, as the radius gets bigger. All right, so let's prove this. All right. So we take some x naught in omega, and we choose 2r so that we get the ball within omega. And then the thing to note right away is our elliptic equation is linear, and it's solved by constants in particular, so that if we have that u is a solution and we have some number n that's constant, then u minus m is also a solution. And that's pretty much the whole trick, so we're almost there. So in particular, we'll do, say, let m equal the average over omega of u. So, or actually, I guess we'll do the average over the ball of radius r. That's right. Of u. Then what we get is, using Cacciopoli's inequality, we are going to get this. Yeah. You want the average over the annulus. I don't think that's true. Yes. Actually, I do think that's true. You're right. Okay. Because, yeah, obviously we're going to use that in conjunction with Poincaré's inequality, so we need it over the annulus. Okay. Good call. So Caccioppoli is going to get us this. Nope. Is that right? Yeah. All right, since u minus m solved our elliptic equation, we get this from Cacciopoli. And then, right, there's like two tricks to get you there. The first one, so here's trick one. And this is a trick that we actually, I mean, I think everyone's kind of familiar with, but we saw in Farhan's talk. So we're going to choose our phi to be, it's a smooth function, compact support. Why I keep doing that on the ball of radius r. And we want it to be radial, and we want it to be identically 1 on the interior ball. So and we want it such that the length of grad phi is bound by 2 over r.
So the support the cutoff is what, right?
Yes. Yeah, exactly. Yeah, we want it. Here, I'll draw it somewhere. Draw it here. We want phi to be 1 in here, 0 out here, and then smoothly descend from 1 to 0 somewhere in here. Obviously, we want it between 0 and 1, and we're going to choose it such that we can bound grad phi by 2 over r. Right, and then, so in particular, something that you're going to get is, since it's constant on the interior ball, grad phi is going to be 0 in there so that we get the support. Grad phi is going to be inside of that annulus, right? It's all just going to be contained in this ring here. Then we have from this that this is going to simplify on the left side. We're just going to get, well, you'll see, this is going to be less than that. So if we just take the energy of u over the ball radius r, obviously that's going to be less than this for our chosen phi. So this is less than or equal to, and now we have, this is bound by 2 over r, so this squared is going to be bound by 4 over r squared. So we can pull that 4 over r squared out. And in here we have, now here, since the support was in the annulus, this is just going to be over that annulus of this. And so we can rewrite this then as something confusing. All right, so then we can just rewrite this as some k times the energy over the annulus of, oh, I see, of, so now using Poincare, right. So now using Poincare, since this was the average of u over the annulus, we're going to get that this all is less than some constant times r squared. So that's going to get rid of our r squared. And now we have constant c times 4 times this constant here. So we'll just call all that k. So here we're going to have what k is dependent on n little lambda, big lambda. Right, and we end up with this. And this is actually pretty much a place that we ended up during Farhan's talk. It's funny because we're just saying when you watch that talk, you get to hear, and then once you know the trick, you're like, oh yeah, duh, that seems really stupid now. But the fancy pants awesome trick is now, prepare to have your mind blown. We're just going to add k times the energy of u over the ball of radius r to both sides. And we're going to get a result, right? So, is there an eraser? So I guess we'll do that over here. So we'll do that over here. So now adding k times the thing on the left here to both sides, we get, we're going to get k plus 1 of them on this side. And on the other side, we have k. K is in both the integrals. Now we have integral over the annulus plus integral over the ball filling the annulus. And here you go, hole filling technique, right? So we got this original one is over this. And our energy here is over this. So putting these two together is going to get us just the integral over the ball of radius 2r. And now dividing both sides by k plus 1, we get our b, which is k over k plus 1, which we see does in fact land somewhere between 0 and 1. Awesome. Right. So there you go. That's the hole filling technique. Now, why is that useful? And what's the whole point here? So let's put it together a little bit. So now we'll use it in something else. I guess I don't need to leave this up. Everybody get that? It seems so straightforward after you've seen it once. You're like, okay, how did no one come up with that before? All right, so now an application. And we're going to use something called Morey's-Dirichlet growth theorem, which says, all right, so let U be a weak solution to our elliptic equation, or actually just let U be H1 omega. And suppose we have constants m greater than 0. We have an alpha between 0 and 1, such that for all balls in omega, that this integral holds, that we have that the energy of U over any ball is bounded by some power of its radius. So if we have that, then we have that U is C0 alpha log omega. Hmm? Yes. Yeah. Duh. Okay. So now everything that we just went through gives us exactly what we want here, right? So if we have that U is a solution of an elliptic equation like we started out with, a weak solution, then here's how we're going to get our bound. And then as long as this bound grows like a power of the radius of the balls in omega, then we get that, in fact, U is even nicer. U is C0 alpha. And the way you do that is just iterating this statement, which I should leave up. So I'm going to erase some of this. Right. So now put E of R equals the energy over ball radius R, hence E, how cute, right? Then using this, you can see it right away. So if we had taken R to be instead R over 2, we would have applied it once, and we would have got B times the energy over the ball radius R. And then we could have applied it again to, assuming that the ball radius 2R is still inside omega, we could have applied it again to this side, and then got this again, and then you would have had B squared times the energy over the ball radius 2R. And so you can keep doing that, right? You can start out at radius R over 2 to the K, and you're going to end up getting, this. You get, if you start with R over 2 to the K, then that's going to be, what is it, K plus 1 e to the 2, or e of 2r, right? And now this is going to imply that that the energy grows like a positive power of our r. And so let's show that. So we're going to say let a be between 0 and 1, but we're actually going to go ahead and choose our a, our alpha, after the fact. So for now, we're just going to calculate forward, and then we'll solve to get the alpha that we want. And pick some big N so that we get 1 over 2 to the n plus 1 times a radius, so that our little radius is between this and 2 to the negative n. Then we get this. Right, and so this follows just from our selection of r in here, and so we just put the bounds in for our r's here, and then using this for here, we get I think. Yeah, that looks right. Okay, so now here, what we want to do is just get that so that it's equal to 1, which we can do. So now choose A, so we can just solve 2 alpha b equals 1 to get whatever that is, negative log 2 of b is our alpha. And so doing that gives us a 1 here, and we just end up that the radius that we have to the negative alpha times this. So our energy over r is bound, or grows like a power of our radius here. And so choosing an r so that the distance from the boundary, so that 2r is equal to the distance of the boundary, we can bound this even better and say, all right, then what? Where am I going to put this? I'll put this down here. Then we can do this. So we'll say let d be right. So given that, we get and this is over omega, right? Because we assume that u was h1 somewhere, wherever the hell we did that. All right, and so in Maury's theorem, we end up with what we want. So we can just put our m equals c, and that's it, and we're done. And then we get a bound for the energy, the growth of the energy over balls of radius r contained in omega. So if u solves our elliptic equation in omega, weakly, then in fact that solution is C0 alpha in omega. Pretty slick, right? Sorry?
You gotta say something about the dimension.
In dimension 2 here. Yeah. Yeah, this is in, I guess it solves it only in dimension 2. I think that this is only solutions in dimension 2. This is only two-dimensional elliptic equations in divergence form. And what else do we get? Oh, and then one last observation is that if in any dimensions, if U is an entire solution, then if it has finite energy, which theorem? This theorem, but I erased it. We ended up at one point where we had this theorem here. At one point we got that the energy was bounded by, it was like a constant times 4 over r squared over the annulus. And this is, Farhan, actually, you showed this last time, right? So if you have that everything's bounded and you let r grow, then obviously you have that, that u is going to be constant, right? So because this is going to be bound for the energy. And I think that you actually did show this in your talk. So r goes to infinity, this goes to 0. And I don't think that's quite enough, but you can show after that that u has to be constant, in fact. So entire solutions to this end up being constant. In particular, in n equals 2, you get the Liouville's theorem. And that's all I have. So there you go. Cheers.